So in week 9 we're going to look at river systems and landforms. So when we talk about river systems, the term that's used is fluvial. Fluvial geomorphology means the study of the shape and the process of river systems. So we're looking at rivers and streams, and we're back to this idea of endogenic and exogenic forces. So we have both actually working on the development of streams. The endogenic forces create the material that's transported. It creates the shape of streams and watersheds, and then the exogenic forces create the water and the other elements that restrict flow, like vegetation or soil types. When we talk about the material that's transported in a river system, the term that's used is alluvium, and we're typically thinking of sand, silt, and clay particles, with clay being the smallest, sand kind of intermediate, gravels, and then boulders in the event of a really big stream. One thing that's needed to really understand a stream system is to understand how they're divided or how they're regulated on the landscape. And they're created based on elevation or drainage basins. So when we talk about streams, we often talk about which watershed or which drainage basin that stream is, and what that means is the area along a certain elevation, it's kind of a dividing line, a ridge or a mountain, where water flows one way or another on either side of a mountain range. And this can be delineated into different drainage basins. So here's an outline in purple or blue. Any water that falls on the inside of this blue line will eventually make its way to the Mississippi River drainage basin. So it's part of that Mississippi River system. And you can divide those into smaller basins depending on elevation. So here is a very small little watershed boundary, and you can see from the shaded relief that this dashed line kind of shows the highest elevation in this local area. Any water that flows on this side of the elevation on the inside line is going to flow down into this small tributary, eventually into the stream at the bottom of the map. Here's another example, kind of showing the mouth of this stream. You've got elevation or gradient causing the downward flow. The drainage divide, again, is this elevation difference between one side and the other. Tributaries are the small little channels that flow into a larger area, and the interfluve is the ground area between streams. So here is another watershed area in green. You can see that they're not always perpendicular to the stream. Again, if you could see the topographic map or a shaded relief map, you would see that in the dark green is kind of the highest elevation point for that drainage divide. And if we look at Oregon, there are many sub-drainage divides or drainage basins. So in Eugene, we're part of the Willamette Basin, and even that can be divided into smaller hydrologic units. The other thing that is studied, or the geometry of the type of drainage pattern. So within the watershed itself, streams will develop different shapes. The most common, if I asked you to draw a stream, you would draw one that looks like, let me see if I can go back up here, that looks like this. This is a kind of a leaf-shaped stream, and it's pretty common. It's very typical stream pattern. But streams develop different shapes, drainage patterns, based on the slope. If it's a very steep slope, it may have one kind of drainage pattern. If it has very eroded or easily eroded rock, if it's a folded mountain, system as opposed to a volcanic mountain system, the shape of the streams or the pattern of those drainage systems are going to be very different. So two I want you to be able to identify are radial and dendritic. And radial forms around a volcanic landform or a central peak or a dome. If you had a butte, you might see radial drainage patterns. Dendritic is the one I showed you earlier. It's very common. It looks like the veins on a leaf. And that happens when you have rock that's very uniform in its sedimentation and layering. So here's two examples. You can see that dendritic has these small tributaries up in the upper right hand corner of this image that join and make the stream, join into the stream as they flow down river. Radial, however, these small little Y-shaped tributaries start up at the top of the volcanic cone, and they don't flow together. They kind of flow out from that circle. And that makes sense when you think about kind of the structure of a volcanic landform. Two other types are trellis and rectangular. Trellis landforms tend to, whoops, let me scoop back here. There we go. Trellis landforms or drainage systems, drainage patterns are seen in folded landscapes. You'd see that a lot in West Virginia, where you have the anticlines and the synclines of folded kind of compressed rock. The mountain systems are parallel, and so these drainage systems almost look like a vineyard trellis, all draining into very short, small linear systems. Rectangular, however, are also formed with some right angles, but they form because the rock is faulted or jointed, and so there are joints within the rock that help structure those streams. So here is let's see, where is the trellis? Here's the trellis. So if you could imagine that this larger stream is at the bottom, but in between two canyons, and on either side of this is the top of a small ridge, and so the water is running from these very tightly folded mountain systems. Rectangular has, you can just imagine vertical and angular cracks in the rock that help support the flow of river systems. Here is an example of the Blue Ridge Mountain system that is folded, and you would tend to see trellis types mountains or drainage patterns there. So when you think about river and stream development, it really doesn't just start as a river. It has several processes of flow that contribute to the development of channels and streams. So the first is overland flow, and this may be uncontained water, just sheet flow, or just kind of flowing, not in any kind of gully or stream. It's just flowing over the ground. As more and more water collects, it may start to concentrate in areas and create small little divots or rills. The rills will eventually be eroded or confined into gullies, and then gullies into streams, and streams into rivers. So there's a process of different types of development into that river system. And so you get precipitation. It truly is a system. There's water flowing underground that contributes to how high a stream system is. You have water coming off the landscape, have evaporation. You have water leaving the system in other ways. So truly a dynamic idea. Another thing to keep in mind is that the work of a stream, in theory, is to get to base level. So as long as and base level in the best of all worlds is sea level. And so a stream starting at some elevation above sea level has got slope, and slope adds velocity and the ability of a stream to do work. And so slope can make a stream have more erosional capabilities. And so as the stream begins to move from high elevation down to low elevation, or the sea or a lake, which is a temporary kind of base level, the stream will cut down, erode, and move material. So we need to kind of think about how streams move that material, what gives them their ability to do work. And so when we look at streams, we want to look at the characteristics of the stream, the physical characteristics that allow it to actually move material. And so one characteristic is the width of the stream, the other is the depth, a third is how fast the water is flowing. And those things, the width and the depth and the velocity of a stream, are often dependent on the slope or the stream gradient. It can depend on the type of rock that the stream is flowing through. And all of those then enable the stream to increase or decrease its sediment load, or the amount of material, stream load, that the stream can move. So when we're looking at a stream, there's some terms you need to know. The thalweg is the deepest part of the channel. So over here would be the thalweg of the stream. And the depth is measured from the current water level down to the thalweg, and the width is measured from the current wetted bankful. Now, maybe this is a low flow summer stream, and so my width might be different than it is, let's say this example is in the spring in Oregon, when we have a lot of water in our stream. So the width might be higher than it would be in the summer if there wasn't as much rainfall and you're measuring, say, down at the notch on the right. So in order to understand how much work a stream could do, you need to be able to measure the width of the stream and the depth of the stream at the thalweg, and that gives you kind of the area of the stream. The other variable that you need to understand the work capacity of a stream is the velocity, or the speed that the water's moving. And there are lots of ways to measure the velocity, and the velocity is typically measured, let me go back up to this slide, about in the middle of the column of water above the thalweg. So the velocity, to measure velocity, you could use a velocity meter or a flow meter, and it gives you how fast the water is moving at that point. Now, there are often meters that are permanently installed in streams at certain points that keep constant measuring, and that way you get really good velocity averages over time. So one thing to remember is that as the water is flowing along this stream, the water that is actually touching the bed has a lot of friction against it, and so the flow rate is not the same through the entire stream. The water here is moving a lot faster. I don't know if you can see this mouse. Probably not. Well, maybe. Oh, I hate to show the yellow mouse thing because it just makes me almost car sick, but we'll do it today because I'm pointing at these slides pretty heavily. So basically, where I have water in contact with the bed of the stream, the flow is going to be much slower. There's a lot of friction. And so where the water column then is in the middle of the thalweg, where it's not in contact with the bottom, the water moves much faster. And that's an important concept when you begin to look at the variability of the water moving throughout the stream. So all of that is to say, you want to be able to know what the stream discharge is, or how much water the stream is moving per unit of time. And typically the discharge, which is what they use the variable Q, is a product of the velocity in the area, and it's measured in cubic feet per second. So what this discharge equation lets you do is predict, if you know what the area and the velocity is, you know how much water will be flowing from that stream system in cubic feet per second. Or if you have a sudden rainstorm and you have a lot more water in your stream, you can figure out maybe what the increased area is. As more water fills the stream, the width gets bigger, the depth gets bigger, maybe the velocity increase, therefore your discharge will increase. So this is kind of a great equation to kind of understand just the relative dynamics. This is a map showing the average discharge. They have cubic meters per second and cubic feet per second, and showing the line width of the amount of water that is coming from these stream systems. And so you see the Missouri or the Mississippi River system has the largest discharge of all the river systems in the United States. The the Columbia River system, sorry, between Oregon and Washington, has the second largest discharge. So you can imagine, my water did not completely fill my canyon, but we're going to ignore that. If you have a stream moving from the image a couple slides back into a much more narrow canyon, it's like constricting your garden hose with your thumb, where you shut off. You still have the same amount of water coming through the hose, but you've shut off or you constrained the pipe that the water's coming through. So if you do that with a stream, all of a sudden you constrict the flow. A couple things can happen is that the flow can back up, but often that flow will go higher up the sides or come out of the bank, increase the velocity. On the opposite side, and then while it increases velocity, it has more ability to do work. The other situation can happen as well. Let's say all of a sudden your stream flows down into a very wide area, and now the width has increased. There's a lot more friction, a lot more water actually in contact with the bed. The thalweg is less deep, so everything is going to slow down, and any material that the stream had been carrying with it will now be dropped out or deposited instead of eroded. So this, in one stream, you can have the dynamics of erosion of material and depositing of material within the same system as it flows from high elevation to low elevation. We also look at streams and try to categorize and identify them by stream type. And there are three major types that you want to be able to distinguish. One is a straight channel, the second is a meandering channel, and the third is a braided channel. And one way to determine if a stream is a straight channel or a meandering channel is to look at a ratio called the sinuosity ratio. And this is basically the linear distance between 2 points on a stream, like as the crow flies, and then the actual, if you were actually canoeing or walking down the middle of that stream, what is the difference between those two measurements. And so I have a couple examples taken from Google Earth. The one on the left is in western Oregon in the valley, Willamette Valley. The one on the right is in eastern Oregon. And the line that you see is approximately, the yellow line is about 9,700 feet long in both images. So I measured the distance of 9,700 feet, and then I used the path tool to measure if I were going to float down the river to the left, how many feet would that be? And it's 19,000 feet. So the ratio is 1 to 2. The other river, if I were to float that, I would only have to go actually 11,210 feet. So the ratio of that is 1 to 1.5. So this stream on the left is a much more sinuous, meandering stream. The stream on the right has some meanders or bends in it, but it's much more of a straight stream. So kind of looking at how those meanders happen or don't happen, you really need to understand the flow characteristics. And so again, the water flowing along the beds, the side of a channel, are going to be slower because there's friction slowing that down. There also may be rocks and roots and other things in the water column. The greatest velocity is below the surface in the deepest part of the channel. And because there is variability within the flow velocity within the stream, it sets up what's called a sinusoidal flow, or almost a spiral curving flow of water within the channel itself. And so if we look at this very crude drawing, I'm just learning how to use the draw tools in PowerPoint, and they're not very forgiving. But anyway, if you look at the image to the right, or up at the top, you see a column of water, and the thalweg is here, and so the fastest water is right here. And as that water flows toward you, it may hit the bank here and have a lot of erosion as that heavier water. It's kind of like you turn your garden hose, again with the thumb over it, against your garden bed. You're going to blow a lot of sediment into the water. The water on the opposite side is an area where the water is moving slower, and so sediment, rock, gravel, sand, has a chance to settle out and slow down. So this side of the stream may begin to build while this side of the stream erodes. Now if you go further down the river, because this thing has a spiral tendency, the thalweg and that column of water, you may see that the thalweg has moved to the other side of the stream. And now erosion is happening on this side and accretion is happening over on the right side. So when we look at stream transport or erosion, it's happening by hydraulic action, again, just the power of water slamming into sediment in the stream bank, and abrasion. So as the water churns up other rocks and gravel, those rocks and gravel hit the sides of the stream as well. And so this is one of the things we looked at with what were they called? When we were looking at the potholes in streams. So you can cause streams to create potholes in the gravel. But so that erosion carves, shapes, loosens by pressure, by shear force, and loosens and lifts material. And once the material is lifted into the sediment, now it's free to do more work. That material can now knock into other material. Rocks can grind upon grind. So it really is, in a way, very much a positive feedback loop. So once the material gets loosened or is in the stream, the stream or river has the ability to transport or move that material. And so the amount of material available, again, depends on the relief or the stream gradient. Is it very steep? Is it very shallow? The type of rocks. Sandstone may erode more easily than flowing over basalt, or flowing over a metamorphic rock that's very densely packed. Land use has a lot to do with stream transport and entrainment. So if you have a lot of construction, if you have people removing vegetation along a stream side, cattle grazing has a huge impact on stream stability and erosion. And so in Eastern Oregon, there's many processes to keep cattle off stream slopes so that the vegetation will grow so streams don't get too eroded. The streams then transport their material in several ways. One is in solution, or a dissolved load, and these are chemicals, limestone, salts, materials that actually are dissolved into the stream column, and if the water slows down or speeds up, it's not going to have an impact on how much dissolved load is in that water column. Suspended load, however, is very fine sediment, silts, and clays that are suspended in the river, make a river look very muddy. That's why they call the Mississippi the Big Muddy, or the Yellow River in China, which has suspended glacial loess sediments, which are very yellow. And those materials will stay in the water column for a very long time. You can go into the Mississippi and dish out a couple cups of muddy water, and it may take days for the sediment to fall out and for that water to be somewhat clear. The other method of transportation in the stream load is called bed load. Oops, did I do? Yeah, I did suspension. So bed load is where material is transported with some contact along the stream bed. So the heavier, bigger material is moved by traction, so it might be pushed or rolled along over time. Smaller material can move by saltation, which is kind of jumping and bumping, where one grain will knock into another and push it up higher into the stream flow, where it'll come to land further down the stream. Now, the size is relative. If I have a stream with low grade and low velocity, it's not going to be able to move very big bed load, and the suspended load may be less as well. If I have a big storm like the one you're going to see in the videos in Colorado, the ability, the sheer discharge from that stream and the velocity was phenomenal, which allowed the bed load size to be huge, so moving large boulders, huge amounts of material. So if you came back and looked at this stream over time, you might see that this grain had now landed here, and that rock maybe had moved just a little bit further downstream. So now that we've looked at how streams are formed, some general information about watersheds, how drainage patterns look, different drainage patterns, and how material is moved in the stream. The second part will talk about actually the landforms that are created from deposition and erosion.